Okay, it's 3 p.m. Welcome everyone to a new episode in our series of Wolfram technology seminars. The topic for this presentation is compilation technologies in the Wolfram language version 13. I gave a similar talk around a year ago, but this time this talk has been heavily updated for what's new in version 13 because a lot of new features have been added to the compiler in version 13. Before we go to the topic of this talk, let's just introduce ourselves. The company I work for is called Unisoftware Plus. It's a small company, technical company based in Upper Austria in a small village called Perg. We currently have more than 30 employees, most of which are theoretical physicists, mathematicians, and software engineers. We've been doing Wolfram technology reselling for many years. Our largest site customers here are the Austrian universities and the Fraunhofer Gesellschaft in Germany. We also have many commercial customers in the German-speaking parts of Europe. The service we provide for our Wolfram technology users is license and installation support. That means we guide our customers through the whole process of ordering Mathematica, setting up the licensing for Mathematica, and doing the installation. And once they have working installation on the machine, we of course also provide technical support in using Mathematica and other Wolfram technologies. But here we are only as good as we can because the Wolfram technology landscape is now really huge, and in many cases we have to rely on Wolfram in the US and in the UK in helping us out when doing technical support. The company also has other business areas. The other one of these business areas is data science, where we are heavily invested in the Java-based Hortonworks big data technology stack using Hadoop and other technologies. But we also do industrial mathematics, where we do classical simulation and modeling projects. And we also do financial mathematics, where we sell our own product line, which goes under the name Unrisk, which offers features for doing financial risks management. But let's now get to the topic of this talk, which is compilation in the Wolfram language. Before we talk about compilation, we have to motivate why we actually need compilation in the Wolfram language and how the compilation is different to interpretation. We will then look at the two different instances of compilation that currently exists in the Wolfram language. One older technology, which is called the lightweight numerical compiler, and one newer feature, which is simply called the Wolfram compiler. The lightweight numerical compiler can produce compiled code for a virtual machine, which is built into the Wolfram engine, but you can also build code for an external C compiler, which will then run this code natively. We will look at examples for both features. Then we will look at the new Wolfram compiler, where we especially look at features which have been added in 13. And we will also look at a new feature which is called the Wolfram data structure library, which is based on the Wolfram compiler and which is also one of the new features in version 13. When we talk about interpretation versus compilation, we have to look at the Wolfram language and its features. The Wolfram language is actually a multi-paradigm programming language, which is based on the following programming paradigms. The first thing is it's a pattern-based symbolic programming language. That means symbols are first-class objects in this programming language. And for example, if I do a symbolic transformation of a plus b squared, of course, Mathematica knows about all these algebraic mathematical transformations that are needed in order to produce the result here. But Mathematica also supports functional programming. Functional programming means that functions are first-class objects in the language. That means I can pass the functions, like, for example, here, the square root function, to another function, like this map function here, and this will then, in turn, apply to a list of arguments. But for programmers which are familiar with lower level programming languages, like, for example, Fortran and C, Mathematica also supports procedural programming with all these regular constructs like for loops, while loops, repeat until loops, and if statements. And for example, I can use this for loop here to simply print out a list of numbers. But this procedural programming is really rarely used nowadays in Mathematica. Actually, if you do good Mathematica programming, you mostly use functional and pattern-based programming nowadays. One other feature that the Wolfram language has that many other programming languages lack is arbitrary precision calculations. This is true for both integer arithmetic and real arithmetic. For example, if here I can do the power from 123 to 123, and you see that the precision of this number goes far beyond the 64-bit representation that my machine supports natively. And for example, for real numbers, we can, for example, do real number calculations with arbitrary precisions. Here, for example, I compute the number pi with around 100 digit precision, and then I can add another number to it, and Mathematica will keep track of the precision and return a correct result. In more recent releases of Mathematica, another feature has been added, which is called natural language input. Here I can use, for example, the insert command and insert freeform input to simply add. This lets me enter arbitrary natural language input, which is then sent out to the Wolfram Alpha system on the web, which will translate it to Mathematica code here. This is also a very powerful feature, which is especially for novices who want to learn about the language. And all these powerful features require that the Wolfram language uses an interpreter for execution and cannot rely on a compiler. And what is the interpreter doing? The interpreter translates the program one statement at a time. And it does not convert these instructions to native machine code, but instead directly works on the source language. This works in the Wolfram language in the following way. The Wolfram language usually passes the Wolfram language input to something which is called an abstract syntax tree, and then it uses rewriting to transform this tree to other expressions by simply applying transformation rules until the resulting expression no longer changes, and this is then returned as the result. And of course, due to the highly dynamic nature of the Wolfram language, each statement makes changes to the state of the system, which affects the next statement. So it's difficult to do really machine code translation of this Mathematica code. A benefit of using an interpreter for the user is that it allows for a very fast development cycle. You enter an interactive session with the system where you don't have to go to this compile execute cycle that you might know from different programming languages. But of course, a drawback of this powerful feature is that the interpreted code runs much slower than if it had been compiled, because the low-level features that are built into the processor of my machine are not used for running the code. Wolfram has, in order to speed up the running of Wolfram language code, Wolfram has decided to add a Wolfram language compiler to the system. And the idea is simply to identify these features in the language which can easily be compiled through low language code. And these features are, for example, machine precision calculations. These are some numerical functions. These are mostly all constructs from procedural programming and some features from functional programming. And this subset of the Wolfram language is then can be fed to a Wolfram language compiler, which creates compiled code which executes faster than interpreted code. And on the very high level code like arbitrary precision calculation, symbolic programming, and natural language input will always be handled by the Wolfram language interpreter. And you see that the inner circle is expected to grow over time, and hopefully at some point in the future, the feature set of the Wolfram language compiler and the Wolfram language interpreter will be the same, and you will be able to use both at the same time. The first attempt at adding compilation to the Wolfram language was what we now call the lightweight numerical compiler. It has been introduced in Mathematica 2.0, which is now 30 years ago, and it has been refined in later version. The idea is to add a Wolfram system virtual machine that executes a subset of the Wolfram language code in a very fast way. And this lightweight numerical compiler creates a compiled function expression that contains a sequence of these sequencing instructions, which are then evaluated on the virtual machine. And this Wolfram system virtual machine is based on an idealized register machine. What does this mean? Let's just look at an example. Here, for example, I run the compile function on a function which is defined on a real Scala value and simply returns this numerical computation here. And I use compile print to show the actual code which is run on the Wolfram virtual machine. And here you see it has some information, and it uses 4 real registers going from R0 to R4 here, R3. And if you look at the instruction, you see that these are low-level instructions, which are somewhat similar to what you know from assembler, and that's why it can be executed very fast and compiled to machine code. This is also true for working with vectors, matrices, and tensors. By simply defining my argument as a one-dimensional vector, I can then, for example, run the length function on this vector and return the result. And if we again look at the compile print output, you see that there are, besides integer registers, real registers, there are also tensor registers in this Wolfram virtual machine. The lightweight numerical compiler has the following features. It supports machine precision arithmetic and most built-in numeric functions. It supports most procedural programming constructs like, for example, if, for, do, while. It supports a subset of the functional programming constructs such as table, map, apply, and fold. And it only supports compilation of user-defined pure functions and not regular named functions. This is a very important restrictions which we will learn about in a few minutes. And in order to learn about the functions that are supported by the compiler, you can use this compiler functions function, which returns a list of all the functions that can be used in compiled code. And you see we have most many numerical functions here. We have some functional programming constructs like outer, and of course we have procedural constructs like while and similar functions here. And if you restrict yourself to these functions, you will you can generate code which will always be compilable in the Wolfram language. The Wolfram system compiler uses a primitive type system to generate its instructions, which only supports numerical types. These numerical types are Booleans, which simply use this syntax here. It supports integers, which using this integer annotation here. It supports real, and it supports complex numbers. And one important restrictions, there's no support for strings, which is unfortunate because many interesting features also in machine learning are based on strings. The lightweight auto-compilation has actually two modes of operation. One is called the auto-compilation mode. In auto-compilation, the compiler kicks in automatically and compiles your code. This is all completely invisible to the user, and we are going to make this visible now by setting these system options here. And it uses some the auto-compiler uses some settings which determine when the automatic compiling kicks in. For example, for the map function, automatic compilation will kick in when the list that is passed to the map function exceeds the length of 100. And similar limit exists for other functions like product, sum, table, and so on. Let's look at an example. Here I have a simply named functions, which is called sum 1000 numbers, which simply takes an integer and then does sums around 1000 different values and returns the result. For example, if we run this on 100, it returns this sum here. And I can, of course, use this function simply in a map function here. And it will do, it will apply this function to the range of numbers going from 1 to 10. And here, automatic compilation kicks in when the list argument here exceeds the defined compile length, which is for map, the default is 100. So let's just try this and do a timing. And you see here what has happened here. Now the compiler, because I've activated this reporting options here, the compiler tells me that the automatic compilation failed because the function I used here is a named function and not a pure function. And then the whole evaluation process then simply forwarded to using the Wolfram interpreter, but normally this is completely invisible to the user. And this means automatic compilation is only supported for pure functions. That means what we can do, we can simply transfer this to a compute function using the function command here, and then using this argument syntax here. And we have a pure function here. And if we pass this pure function here to the map function, you now see that we do not get an error message from the automatic compilation process. And also you see that the result here has computed in a much faster way than the original function here. And this is very important to keep in mind. Use pure functions so that the automatic compilation will do most of the work for you. The other mode of operation is manual compilation, and manual compilation is also easy to use. And the good thing about manual compilation is that most textbook algorithms can be written in a style which is compatible with the Wolfram Language compiler. For example, here for this example, I have simply copied the following pseudocode from the Wikipedia page on the insertion sort, which is a very simple sorting algorithm, which is also used, for example, as a basis algorithm in more elaborate sorting algorithms like quicksort. And here I have this pseudocode here, and we can simply translate this pseudocode to language, to a Wolfram language code pure function, which looks very similar. There we only have to make the following adjustments. We have to add a module for scoping in order to be able to declare local variables. And the other change of note is that we have to change the indexing from 0-based to 1-based, because arrays in the Wolfram language are 1-based. And I simply took the short route and simply added 1 to each index, which was originally used in the original code here. And now once we have defined this function here, we can then simply run it. And you see it seems to work. It sorts the input list here and returns the correct result. One interesting thing about this code is that it's completely type agnostic. The type the function works with lists of different types. For example, I can use it. We've used it here on integer numbers, but we can also use it on integer numbers here. We can use it on real numbers, for example. It works with huge numbers, but the function does not work, for example, with complex numbers, because comparison is not defined for complex numbers. If we run the function here on a list of complex numbers, the result will be actually returned unevaluated. And why did it fail? Because if we look at our implementation here in this comparison here, we used the greater operation, and this is not defined for for complex numbers, and that's why this this function call failed. So the whole system is based on structural compatibility, not on typing as we know it from other programming languages. We can now use the compiler to target the Wolfram virtual machine, because the interpreted execution of this function is pretty slow. Let's just run this function on a list of 1,000 numbers and random integer numbers going from 1 to 100,000. Then let's check if the output is ordered and let's measure the timing of this thing. And you see that it's very slow for this small list. It takes more than half a second. If we compare this with the built-in sort function, the built-in sort function takes less than a millisecond to execute. And let's use the lightweight Wolfram compiler now. And the code that needs to be compiled needs to be annotated with type information. That means we create an insertion sort compiled function. And this compile function here will work on machine-sized integers. And we use this syntax here, which describes a machine-sized integer vector. This is the first one, is the argument here, is the type range, and this is the actual rank, which is one dimension for a vector. We then simply call the insertion sort function in this compiled implementation here. And in order for this symbol to be looked up, we have to set an option here, which says inline external definition, set this to true. We set the compilation target to the Wolfram virtual machine. That means the target code will be created for the Wolfram virtual machine. And we had set the runtime options to speed. That means we optimize for speed rather than quality of the result. This gives us a compiled function, and we can now use the same examples on our compiled version of the function. For example, if you use it on a list of integers, you see that the compiler now gives us a warning that the compiled expression was packed to rank 1/10 of machine initializer in order to be called, and then the compiled function was executed. If we try to run this function on rational numbers, for example, the compiler tells us that this argument, the position 1, should be a rank 1/10 array, and thus this function cannot be used in compiled form. And what the Wolfram language does here, it simply proceeds with regular interpretation of the function, and it returns the correct result by interpretation. This is also true for real numbers here. But for example, if we use real numbers which are actually integers in disguise because they have no fractional parts, you see that the compiler is really clever enough to convert these input to an integer input. And here you see at the result that it returns an integer list here, and not a list of reals as we see above. And let's compare the performance of the interpreted versus the compiled version. Our interpreted version was very slow, always more than half a second. And if you use the compiled version here, you see we have a drastic speed up, going from half a second to less than a tenth of a second. But we can go beyond the Wolfram virtual machine by targeting an external C compiler. By simply setting this compilation target argument here that we used here to C, we instruct the compiler to create code for the C compiler, and this creates C code, which is then compiled with an external compiler. This external compiler needs to be installed on the machine. And this external compiler is instructed to compute a shared object, and this shared object is then linked back to the Wolfram kernel, where it becomes part of the kernel code and is almost as fast as built-in kernel code. And the interesting thing is, the way this works is that the Wolfram goes through different stages, and it uses different features of the Wolfram language by going through these stages. It first uses the Wolfram language function source. It then uses the Wolfram lightweight compiler to create symbolic C code. Symbolic C code is a representation of C code that is written in Mathematica code. And using this symbolic C code, it then creates a library link C source code, which is then forwarded to the C compiler driver package, which looks at the compiler installed on the machine and produces the shared library, which is then linked back into the kernel. And one drawback of this whole thing is that it only works if a compiler is installed in the system. This is usually not a problem with Mac OS 10 and Linux machines, but on Windows you have to install, for example, a Visual Studio in order for this to work. Let's just look how this works behind the curtain. I just enable some logging output here, and let's just create native C code here. And I have again my compile command, and here the only changes that I make is set the compilation target to C here. And if I do this, what Mathematica does, it actually launches the compiler installed on my machine and produces a shared library object, which you can see here. And the source code that is produced is stored in this file, and we can now inspect the source code here. And you see that it's actual C code, which is very similar to the the Wolfram language virtual language machine code that we saw earlier. It seems some low-level code which uses a lot of go-tos and very basic integer arithmetic here. And of course, this native function can then be used in a similar fashion, and it is subject to the same restrictions as the original Wolfram virtual machine compile function. That means the action arguments are converted to the integer tensor, and if this is not possible, again, Mathematica reverts to using the interpreter and does not profit from compilation. Let's now compare the interpreted code, the Wolfram virtual machine compiled code, and the C native code for its performance. We use a bar chart and simply run some timings on a random integer list of size 2000. And we then produce in graphics here. And you see this graphics here shows us that going from the interpreter to the lightweight Wolfram virtual machine already produces a speed of more than 90%, and then going from the lightweight virtual machine to the native compiler adds another order of magnitude optimization. And you see that really compiling Wolfram code is really profitable, and you should try to use it in your existing code. Okay, let's now turn off all the logging features here and move to the more interesting part. The Wolfram, like the lightweight numerical compiler, has some restrictions which make it difficult to extend it to more elaborate features of the Wolfram language. And therefore, Wolfram decided on creating a new compiler, and this they started a project almost 6 years ago. The first release of this Wolfram compiler was in version 12, and it has been heavily updated in version 13. This compiler provides advanced compilation capabilities compared to the lightweight numerical compiler. It's a very ambitious project whose goal is to translate an increasingly wide range of Wolfram language code into native machine code. The Wolfram, lightweight numerical compiler will not be extended. All the effort into compiling Wolfram language code now goes into the Wolfram compiler. The Wolfram compiler introduces a comprehensive type annotation system and type inferencing system into the Wolfram language, which is also interesting if you use it on its own and without looking at the compiler. On the back end, the Wolfram compiler is based on a technology which is called LLVM, which stands for low-level virtual machine. And this low-level virtual machine is like, I would say, a compiler framework, which is nowadays used for all modern programming languages. For example, programming languages like Rust, which have been invented in the last 10 years, they all use this low-level virtual machine as a compiler backend, because this compiler backend is capable of producing machine code for all modern architectures, like, for example, Intel processors, ARM processors, but also more exotic architectures like, for example, CUDA, OpenCL, and also WebAssembly. And there are basically two functions which have been added to the system. One is called function compile, and this generates a so-called compiled code function expression that contains the compiled code. The whole Wolfram compiler is still marked as experimental features and not fully documented at the moment. And so many of the interfaces are subject to change. Let's just look at a simple usage of this compiler. As I mentioned, the compiler introduces type annotations, and these type annotations are now really first-class objects. That means they have a typed, head, and they simply associate a certain argument with a certain type information. And here you see the implementation of the function. And I can simply invoke this function as expected. And one important thing is the Wolfram language interpreter ignores these type annotations here. That means I can freely evaluate this function on real numbers here, and it will return the expected result. These pure functions can then be compiled with the new Wolfram compiler using function compile. This gives me a compile function, and these compile functions can be evaluated for integer arguments. And one important difference here, the compiled function enforces these type annotations that have been given here. That means if I evaluate the compiled function on a real number here, you see that it gives me a failure message because this 1.2 is not a machine integer number, and my compiled functions only runs on machine integers. And you also see that here there is no fallback to the Wolfram interpreter. It simply returns a failure result. And this is different to the old compiler, which simply continued with Wolfram language interpretation. The Wolfram compiler type system is a very elaborate type system. Typing is done by annotating pure function arguments with type information. And these type annotations already mentioned become first-class objects in the Wolfram language. These type annotations are simply advisory to the Wolfram language interpreter, but are enforced for compiled Wolfram language code. If I have a non-type function here, for example, I can use then basic type annotated pure functions. And these basic types support integers, reals, unset integers, booleans. And if I look at the documentation here for the type command, you see the list of all basic types, which are all types which are more or less supported by the target low-level machine that the code is being compiled for. But you also have support for compound types. These compound types use the type specifier notation here, and this type specifier notation is currently supported only for packed arrays, which are which lets me use vectors, matrices, and other tensors of certain rank, and for numeric arrays, which are simply a more modern form of these packed arrays. And if I, for example, compile this function here on an array, you see that this function works on the array, and the fold operation is completely supported on this packed array here. The same is true for this numeric array, and numeric arrays, of course, work in the same way. In version 13, a new compilable list type has been added to the system, which is called the so-called list vector. A list vector is similar, is a compiled form of the regular list that Mathematica supports, and that means that the actual element type can be itself be as a type. For example, I can now simply define a type specifier, which is a list vector of strings, and this gives me a function which can then be invoked on a list of strings. This is currently not documented and probably also subject to change, so I would not advise on using it in your own programs. Let's just look at a Wolfram compiler example here. Let's rewrite our insertion sub function as a pure function with type annotations for the new Wolfram function compiler. Here I have to change the type annotation of my function here to use this type notation here. I'm using simply a packed array for integers with the dimension 1. That means it's a vector, and the implementation is copied verbatim here. And I can now simply compile this function here using function compile. This takes some time and returns as the compiled function. And I can then use the original function, but I can also run the code on the compiled function. And again, if I try to use this compiled function on inputs that are not that do not follow this type specification given here, I will get an error message. And let's now compare the interpreted code, the lightweight virtual machine code, the lightweight C code, and the Wolfram compiler code for performance. Let's just do the same random test here. We create a random integers of length 2000 in the range from 0 to 100,000, and we run all the different compiled functions that we have created for now. And this creates the following bar chart. And here you see that the new Wolfram language compiler is currently not as fast as the lightweight virtual machine or the lightweight native machine. because it's currently a work in progress, and there are plans actually to compile the compiler which helps in order to make it faster. One interesting feature which has been added in version 13 is a feature called function declarations and compiler environments. And in my view, these two features drastically improve the applicability of the new Wolfram language compiler in your existing Mathematica code. What are these features? A function declaration allows for the clear separation of a declaration of a function and implementation of a function. A function declaration associates a name with a type signature of a function and an implementation. And using many function declarations, I can now then create a compiler environment, and this compiler weight is simply a collection of function declarations for use in compilation. Let's just look at an example. I used the new built-in function create compiler environment to create one of these compiler environments. And once the compiler environment is created, you see that it has currently no functions in this in here. We have now our original pure definition of the insertion sort. Let's just print it here for reference. And we add another pure function which is called merge sorted to merge two sorted lists. And this function here is a simply merge function which takes two lists as an argument and then goes to each element and copies the larger element, the smaller element to the output list. And so it's actually a function with linear complexity, and then it simply returns a list which combines with the combined size of both lists, which is then expected to be sorted. And what we now can do, we can add both functions for integer arrays and add them to our compiled environment. How do we do it? We use compiler environment append2 and pass in our environment here. And here we now have to use this new feature, which is called function declaration. This function declaration associates our implementation given here under a certain symbol name, which is simple. I simply use the arbitrary name insertion sort int here. And here I'm actually having the type signature, and this type signature describes that the function insertion sort shall be compiled going from an integer vector and returning an integer vector. And this uses the special syntax using this rule syntax here, where the signature on the left side of the rule you have the parameters of the function, and then on the right side you have the type which describes the result of the function. If we look at the merge sort int function here, we can also add it to our environment. And here the type specification looks a little bit different. We have two arguments, two vectors of type integer 64 here, and the result is again a vector of type integer 64, and we apply this here to our merge sorted implementation. Please note here that we simply use these completely pure functions here, and that means we have a complete separation of declaration and implementation, so that we can really separate the compilation process completely from our implementation process of our functions. And if we add this to our environment, we have now two functions in our environment. And using this environment here, we can now use function compile to use these declared functions in another compiled function. How do I do this? In function compile, I simply instruct function compile to use my compiled environment, and this gives my compiled function access to the merge sorted int functions and to the insertion sorted int functions, which are part of the environment. And I can simply, and this was what does this function do? It simply merges a list of lists. And how does it do that? It does this by simply doing a MapReduce function. It simply maps the insertion sort function on each sublist, and then merges all these different sorted lists by using a simple fold operation, which uses which goes to the sorted list by merging two sorted lists at a time. And if I have this sort merge function now, I use function compile to compile this function. And what Mathematica now does, it creates using the information from the compiled environment and using this definition here, it creates a complete compiled function, which is now controlled sort and merge, and operates on actually on a list of lists. And you see this because here we have dimension 2. That means the function that is being compiled here will works on a vector of vectors. This gives us the compiled function here, and I can now use the sort and merge function, and it will happily sort a list of lists. And for example, I can, if I add another additional elements to this list here, you see that it does the expected thing, and it does this all in a completely compiled fashion. So the great thing about this function declarations on compiler environment here is that it lets you build up your compiled function in a bottom-up way, where you start out with simple functions. You add these functions to your compiler environment one at a time, and then build up other compiled functions, make use of this function, and so you have a complete control over the environment where the compilation is done. And this also frees you from the necessity to use nested functions all the time, because with earlier versions of Mathematica, you had to, in order to use the compiler, you had to write many nested functions. Now you're free to add these nested functions to a compile environment and use them directly in higher level functions. Another feature that's new in 13 is the Wolfram data structure library. What is this? This is a Wolfram language edition which provides support for a number of key data structures. And these data structures are completely implemented with the Wolfram compiler. That means they don't run interpreted Mathematica code. They run compiled Wolfram language code. And these data structures add mutability to the Wolfram language. And this mutability, although it's something which is dangerous in many programs, if you want to write fast programs, mutability cannot be completely avoided. And these data structures can be also integrated into compiled code. Which data structures are currently supported? Simply evaluate the $data structure symbol here, and you see we have data structures for trees like binary trees, balanced trees like AVL trees. We have arrays like here, like a fixed array. We have linked lists. We have hash sets, hash tables, immutable vectors, KD tree queues. We have, for example, a priority queue, and these are all implemented in a very efficient way. Let's just look at a linked list for an example. This creates a linked list data structure, and if we look at the information on this data structure, this information gives us information on which operations are supported for these kind of data structure. The data structure linked list, for example, so it's append, copy, drop all, drop first, and so on. That means, for example, we can use the append function here, using the syntax here to append values to our list. This changes the list in place, and now the list has a length of 3. And we can use, for example, this nice visualization here in order to see what the visualization is. And using the normal function, we can convert this low-level data structure to a regular Mathematica list. And the great thing about this data structure is that they are much faster than the regular Wolfram language list. For example, if we use a normal Wolfram language list here and use the append to function, which corresponds to this append we used here, and do this for 3,000 elements, what we see here is that this actually is a very slow operation. Why is it slow? Because the Mathematica has to make a copy of this list every time it does an append, because the underlying data is immutable and cannot be modified. This is not true for our linked list data structure. Here we can simply modify the existing structure in place by simply appending the new element to the end of the list, and you see that it's much faster than using the regular immutable Wolfram language list. And so simply by using for certain complex algorithms which need to go faster, you can simply switch from using a regular list to, for example, to this new data structure list. This will already give you a speed up without having to go through the compilation process. But of course, these data structures can also be used in compiled functions. And this we will try to use this as an example, and we will use the built-in priority queue data structure, which is also known as a heap data structure, to implement a heap sort in Mathematica. And how is this done? You see here I'm declaring a function here, which simply again operates on an integer vector. Here I'm adding a module for the implementation here. And here, a heap sort is actually a two-pass algorithm where we first create a heap data structure from the input. You do this by simply creating a priority queue data structure, and then using the push operation, adding all the elements from the list to a heap data structure. And once we have done this, we use the pop operation from the heap to extract the largest element from the heap every time we use pop. And since this gives us the large X, and this we then create a fixed array. This fixed array will then hold the sorted result. And we have to do this going in a reverse fashion because pop gives us the largest element. This largest element goes to the end of the list. And we then iterate from the last element to the first element until we've reached the first element, and therefore, so we get a regular sorted list, and then we simply use the normal function to return the regular sorted list. While I was explaining this, I have compiled the function in the background so that we can now use it in the regular heap sort function works as expected, but also the compiled function should be giving us the same result. And you see here, if we now compare the performance of the uncompiled function with the compiled function, you see that it's more than an order of magnitude faster, which shows us that these data structures are completely implemented in terms of native code. And using these data structures together with compilation, you can build up very elaborate programs completely in the Wolfram language in a completely new environment without having to use the regular Wolfram language structures. And actually, if you have some background in programming, you probably know that many problems can be reduced to using one of these data structures here. So you are completely covered because there are only a few of those are still missing, but Wolfram works on adding new data structures with each release. So let's sum up and sum up the pros and cons of these different compilation technologies that we have in the Wolfram language. We have the Lightweight Numerical Compiler targeting the Wolfram virtual machine. This is a very mature technology which has been around for 30 years now. One advantage of it is it works in the Wolfram cloud, and the compiled code is good enough for many scenarios. The problem is it's restricted to numeric types. For example, if you want to use strings, this will not help you write faster code. The Lightweight Numerical Compiler can also be used for targeting a native C compiler. This is also a very mature technology which has been around for, I think, 15 years or so. It generates the fastest code at the moment. And it profits from C compiler advancements because it's actually based on using an external C compiler, and these C compilers go to new releases every year, which make them faster. You profit from these compiler advancements as well. It's restricted to numeric types. The drawbacks, of course, is it requires a C compiler installed in a system. That means if you have a notebook that uses that compiler, you can not simply give this notebook to a coworker which doesn't have a C compiler installed on his or her system. So this is really restricts the general applicability of this technology, and of course, it does not work in the Wolfram cloud. Many of these restrictions have been lifted for the new Wolfram compiler, which is available since version 12. One of these the benefits of the Wolfram compiler is that it's under active development and it gets better with each release. It works in the Wolfram cloud. It supports non-numeric types. For example, strings are completely supported. It enables you to future-proof your Wolfram code to run in future in environments like GPUs and WebAssembly, because these backends will be available at some point in the future in the Wolfram code. And the drawback of the Wolfram language compiler is that it's experimental technology and is subject to change. The compilation process is somewhat slower than the older compiler, and it's not fully documented yet. And many features are simply documented in YouTube videos, which I consumed in order to prepare this talk. And finally, let's sum up some Wolfram compiler best practices that I try to apply to my code. The first information is that well-written pure Wolfram language code is fast. That means if you use an appropriate representation of a problem in Wolfram language code, there's usually not much need for using a Wolfram compiler, because the Wolfram language has features like matrices. It has features like graphs, like trees, like images, like videos. And if you use these appropriate representations of your problem space for the things you do, you will profit from the built-in high-level functions, which are usually faster than the self-written lower-level functions that you write in Wolfram language code. Also often overlooked in Wolfram language code are features like sparse arrays and listable functions, because when you're dealing with large data, most of the time this large data is sparse. So using sparse arrays, which are very efficient in the Wolfram language, let you work with large data in the Wolfram language. And there's a very good mathematical exchange question here, which I have linked here just for reference. When you all receive this notebook here, you can go to these questions and look for interesting hints on performance tuning. Another important information is that code compilation should not be an afterthought. That means that you should start from the very beginning. You should write the code from the very beginning in a fashion that makes them compilable. That means prefer pure language functions over named functions, because these pure functions auto-compile, and these pure functions also can be easily compiled either with the old technology or the new technology. And with the new technology, you can simply augment this with type hints by using these function declarations and adding them to a compiled environment, and they will magically be compiled. And finally, these Wolfram language data structures offer much of the benefit of compilation. That means before going to the process of compilation, try to find a Wolfram language native data structure, which probably solves the problems better than going to your own and doing an implementation of your own data structure in Wolfram language code. Okay, here I've also collected some online resources on the Numerical compiler. Here some tutorials. The Wolfram language compiler, which is unlikely not very comprehensive documentation, is available at the time. But there are, as I already mentioned, there are good YouTube videos. For example, these two videos here are from the recent Wolfram Technology Conference from last year, and they go beyond what I have explained here. And then there's also the Wolfram data structure library, which is documented here. And we also have an interesting mathematical stack exchange that deals on using these data structures in function compile. Good, this brings me to the end of my talk, and I thank you all for your attention. And maybe we have some questions, and maybe we have some questions regarding using compilation in Mathematica code.